And I think we're gonna go ahead and get started here with a little bit of an introductory lecture and a little bit of exploring through the new book system, the MyLab Mastering. So just want everybody to kind of see. I think I figured out a little bit of a system that we can work through this semester without having like an actual textbook, but still without doing like a whole bunch of lecturing. I'm going to do a little bit from the first PowerPoint today, and then we'll kind of look at what Pearson has to offer. So, starting off with the PowerPoint, like I said, we're talking about natural hazards. So we're going to go back through a lot of the stuff that we've already talked about from last semester, just more focused on humans and how they affect humans, what's going on there. And so we've got a little bit of terminology and we've got a little bit of overview to look at the beginning of this PowerPoint. So first off, they have learning objectives. I have the PowerPoints posted online, so I'm not going to go ahead and read through all the learning objectives. But in a big picture sense, we want to look at all the different processes that are going on the earth and directly how they affect us. This is kind of a selfish human semester where we're like, yeah, tornadoes and earthquakes are good and everything, but how does it affect me? How does it affect my house and my life and my city? That's what we're looking at for natural hazards and disasters. So, one of the things these PowerPoints do, and we're not gonna go like slide by slide through all the PowerPoints, but I probably will do all the PowerPoint chapters because every single one starts with what they call a case study. And this is something that's pretty common in science. We will talk generally about a broad subject, and then they go into your case study, which is a very specific real world example of that. And so for like, I guess this would be like your earthquake slash tsunami case study if we were in that chapter. The Haitian earthquake that happened, was this 2010? I don't know. Sometimes these things get a little bit further back. We're like, I don't remember those so much, especially here in high school, because 10 years ago, y'all were pretty young and maybe not paying attention to whether there's a Haitian earthquake or not. But this stuff is real life relatable, and so we're gonna go through the case studies for every chapter at the very least, if not to get a little bit of overview. And actually, at the end of the year, our signature assignment will be everyone in class picks a chapter and does a little report on that particular case study. So one chapter is going to be like earthquakes, another chapter is going to be wildfires. And so you're going to take that specific event that they had for that chapter and kind of expand on it a little bit in a report. So their example here is the Haiti earthquake. Oh, I guess I didn't read the title up here. It was in 2010. This was pretty bad. This was a really bad earthquake. It caused a lot of damage in their country. Um, and they kind of talk about what led up to that earthquake being so bad for Haiti comparatively to other earthquakes that happened. And so it wasn't just the earthquake, it's basically a lot of things that kind of compiled on top of it. So Haiti's population increased dramatically in the recent decades. About 90% of the country was deforested. The island was vulnerable to hurricanes and other high intensity storms, as well as earthquakes. And basically, they got a whole bunch of all this stuff all at once. Four hurricanes and tropical storms hit the island within a month's time. 2 years before the earthquake. And so they were still recovering from all these hurricanes that happened about 2 years ago when the earthquake struck. The cities were overcrowded because of their population increase, because of the deforestation. Their foundations on a lot of their towns and hillsides were not stable. And so the earthquake caused a lot of mudslides. It caused a lot of buildings to be knocked down. And their building codes weren't necessarily up to par. And so there was a lot of damage and destruction, probably more than there should have been if they had kind of been on top of things. Well, we've been there too. So here's a picture of a Haitian hillside that's obviously been deforested. You would want to see trees all over this entire thing. And you can really see that with this hill, there's nothing to hold it into place. You have a really heavy rain like a hurricane, or you have an earthquake that's more likely to cause a landslide. and there's no like root systems established to hold all this material in place. So you're not going to have a good time when that happens. So they basically talk about how the earthquake became a catastrophe. 85% of people in Port-au-Prince lived in slum conditions, so not great building conditions, sanitary conditions. Poor conditions led to 190,000 destroyed or damaged homes, killed 250,000 people, 2 million homeless with poor sanitation and water quality. And so you can see it's less about the earthquake itself and more about what happened to the people after the earthquake. That's really what we're looking for. Why did these things happen? What could we have done to reduce the catastrophe that this was? And what kind of things are reasonable to put in place in these parts of the world? Because it's easy for someone from the outside to look and say, you should have done this, you should have done that, you should have done this. But what kind of implementations can actually be done in real life for these people in this country? So they're saying the reason for this catastrophe was clear. It was a heavy human footprint, a large number of poorly constructed buildings, and the population grew very, very quickly. And this is the picture I was looking for. I was wondering if it was in last semester's uh, slides or not. This, I believe, was like the president of Haiti's house. Like this is like the White House essentially for Haiti. And so one of the nicest buildings in the country, or at least what should be one of the nicest buildings in the country, sustained an immense amount of damage. You can see the top layer collapse.
Singers report to the stage. Grant Cruzan, Andrew Leach, Dan Lancome, Jake Osborne, and Parker Step.
Nice. Don't forget to smile. Are you going mask down or mask up?
Mask down.
Oh, really? I'm going mask up just to preserve the year. I mean, it is what it is. Yes.
Is it okay if I go with them?
They didn't call you.
They skipped P. They skipped P.
It sounds like they might just be doing all boys, right?
Yeah.
It's all boys they called, right?
Yes.
So maybe they're doing all boys because don't they have like the fake tux they put over the guys?
Yeah, I don't know what order they're doing it in, because then they just went back to C for Grant.
Yeah, I don't know. Just wait a little bit. They'll get you. Trust me, they want everybody to take their picture. Yeah, I think I'm gonna leave my mask up for the picture because we've had masks on all year. Gonna commemorate the year. Okay, let's see. So why study natural hazards? Their example for why studying natural hazards isn't maybe the greatest. They're expensive. They cost us a lot of money, and it affects our life quite a bit. And so the more we understand about them, the more human lives we can save, the more money we can save, the more we can progress without having to like rebuild all of our houses and recover from this kind of stuff. So recently, I guess they're saying since 1995, we've had the deadliest tsunami caused by an earthquake in the Indian Ocean. We've had tsunamis in Japan caused by the largest and costliest earthquake in recorded history. We've had catastrophic flooding in different areas of the world, volcanic eruptions that shut down international airports, the worst tornado outbreak in U.S. history. And this has all been now, which is quite a while, but in the last 25 years. And so a lot of stuff really has been compiling lately. And maybe some of these things aren't technically worse than they used to be, but we have much more people in the way. Like that's one of the things about Texas. We have tornadoes in Texas, right? Does anybody know someone who's been like had their house knocked down by a tornado? Yes, but not everybody, because while there's a lot of people in Texas and we have a lot of tornadoes, there's also a lot of empty space. And so the vast majority of our tornadoes in Texas don't cause a lot of damage. They just go through rural areas and don't end up destroying a lot of stuff. I did live through a tornado in Lancaster, and so yeah, I know some people that have had their houses knocked down. And actually, when I was at OU, there was one of the really, really bad tornadoes up in Moore, Oklahoma. So my wife was out at work that day during that one. So Tornadoes are pretty crazy, but we'll talk about those later. Let's see. Processes, internal processes and external processes. Internal processes come from forces within the earth, generally going to be plate tectonics. External processes come from forces on the earth's surface, usually generated by the sun. So pretty much all weather is because of the sun's energy. And so you have kind of like weather in this category, or weather related hazards, and then earthquakes and volcanoes, and that's probably about it for this one. So they're kind of grouping them into internal and external processes. So now here's the key part that I wanted to get to. A hazard is a natural process or event that has a potential threat to human life or property. It's not a disaster until humans make it a disaster by being there. For instance, the tornado example. A tornado goes through one of the farm fields out here, and doesn't destroy any crops and doesn't destroy any houses. It was a hazard. It was hazardous. It was a bad thing. It was a natural event that happened, but it wasn't a disaster because literally nothing got destroyed except for maybe some trees and a couple plants. Now, if you put a whole neighborhood there of houses that maybe aren't necessarily constructed very well, and houses get destroyed, people get killed, now you have a disaster. And so the natural process doesn't really make it a disaster. Humans being nearby and getting our stuff destroyed is what really makes it a disaster. So criteria for disaster: 10 or more people get killed, 100 or more people are affected, state of emergency is declared, which is usually something we kind of wait for. Did the president declare a state of emergency? Did the governor declare a state of emergency? That's kind of an indicator of how bad things are. And then international assistance is requested. Are other countries like, oh, you probably need some help with that? You might have a disaster on your hands. And then if it gets even worse and things like snowball and you have a bunch of stuff that probably shouldn't have happened, but you didn't really plan and prepare very well, now you have a catastrophe on your hand, which is a massive disaster that requires a significant amount of money or time to recover. More than likely, you could probably categorize the COVID outbreak as a catastrophe. The amount of money that we're going to spend on it in total, the amount of people that have died, the change to our overall lifestyle is going to be pervasive for years. And so that's something they actually don't talk about is biological agents, because it's not really geology related, but you can throw it in there. And then I like this map. This map has a little bit of everything on there. We've got flooding in blue over here. We've got tornadoes in green. We have earthquakes in yellow. We have hurricanes in light blue and purple, which if you're making this map, maybe don't have blues and blues. I know they're different blues, but maybe pick a different color set. Landslides in like your weird green yellows, and then some volcanic hazards. So you can kind of see which part of the countries have which stuff. Here in north central Texas, I'd say that's probably a little bit underreporting our tornadoes. We should probably definitely be in the green here for tornadoes. But we don't have a lot of hurricanes up here, at least in North Texas. Down in South Texas, you can get some hurricane action. But no hurricane action for us, no earthquake action for us. We don't really get wildfires or landslides or anything other than tornadoes here. So we're not in too bad of a part of the country if you're into living and not being in a disaster. It's not too bad. Although it's really hot in the summer, and that sucks. So I don't know, maybe you'd like to live somewhere else. Over here in California, got to deal with all sorts of stuff. But the temperature is apparently pretty nice most of the year. So they go into examples, which I don't know that we need to get into too much. Couple trend lines. I think we're good here. These charts are all right. They're basically saying, what is the potential for humans to make this worse by just being there and being humans and doing their stuff? So like floods, occurrence influenced by human use. Yes, like we influence floods. We dam up rivers. We make lakes. We pave over fields and make parking lots out of them and build new neighborhoods. And all of a sudden, stuff floods where it shouldn't flood before. We build our houses on the side of lakes and streams and stuff. Later this year, I'll show you when we talk about subsidence and landslides. I don't know if we did this last semester. Did I show you the lake that fell into, or the house that fell into the lake here in North Texas? Yes. Okay. Maybe I'll show it again, anyways, because they set the house on fire. It's like a burning house falling into a lake. It's nice. But yeah, we definitely can cause floods. Can we cause what? Hold on. Occurrence influenced by human use, earthquakes. I don't know about that. How are humans going to influence an earthquake? Occurrence influenced by human use.
Like
Fracking?
Yeah, I don't know. Maybe that's. I feel like at the very least that demands a perhaps, but probably not like a hard yes on that. And so, anyways, we don't need to go too deep into that. How much time do we have left in class?
13.
Okay, not too bad. So real quick, what I want to show y'all, if you go into, and you don't have to do it right now, but this is something I'm going to try to do in class to kind of get away from the PowerPoints. If you go into the MyLab Mastering, click Open MyLab Mastering. It takes you to the Pearson page. I believe one of the things that you can see from here is this study area. So click on the study area. If it opens up, and it'll say access the study area. And it's basically, if we go back and read this, access the study area to watch videos, animations, take practice quizzes, and more. Your work in the study area does not report to your instructor's gradebook. To complete instructor inside activities, go to assignments. So basically, this is like an extra area where you can get extra content, do practice quizzes that I don't get to see them. It's for you to practice. It doesn't show up in the gradebook. That's just how it's going to work. So if we go to chapter 1, they've got a couple videos and animations here. And I just wanted to go through those just to let y'all see them and kind of talk about them for a second. So they have this Earth's hydrologic cycle. Let me see. They talk a little bit on it, but.
Describing the distribution of fresh water and ocean water on Earth. Of all the water on Earth, more than 97% is contained in the oceans.
Yeah, let me fast forward.
The Pacific Ocean contains and the Atlas fresh water.
Okay, so I don't want to listen to all this, and I don't know why they started off with water a little bit, but it's a fairly good video if you were to watch it all the way through. They give you the breakdown. 100% of all water, where they have it broken down into 97% is in the oceans, and just this little tiny 2.78% is fresh water that we can actually drink. Of that fresh water, most of it's on the surface. You got a little bit in the soil, a little bit in the ground, and a little bit deep in the ground in your groundwater. But a whole bunch of it is at the surface where we can actually access it. Now, out of the stuff that's at the surface, I can move my mouse here, 99% of that is ice and glaciers, which we do not have access to. I mean, we have access to, but melting water for drinking is not reasonable to do. And so of the surface water that's actually fresh that we can drink and is easy to get to, only like less than 1% is actually drinkable water in freshwater lakes, slightly salty lakes that we can maybe take the salt water out of, in the atmosphere that will eventually turn into rain, and then rivers and streams which we can dam up and make more lakes out of sometimes. So it's a pretty interesting little chart. They have a nice actual cycle chart, which in a second,
As the animation finished,
it kind of goes live. Let me mute here. It kind of goes live, and you can kind of see how everything moves around, which isn't too bad. It's a little bit better than just a standard picture. Yeah, it's got everything on there. We're all familiar with the water cycle, though. Something else they kind of go through is phase changes from solid to liquid to gas, and what that means for your molecules. In a second over here, you'll have like a little molecule window show up. And I think it does a good job showing your latent heat. which is the heat that happens in between two different phases. So like when I'm going from ice to liquid or from liquid to vapor, there's a period where my temperature stops changing, like it stays at that same temperature until all the ice is melted or until all the liquid has boiled away. Then once I change all of it over to a different temperature, I can start to change temperatures again, or change it over to a different phase. Then I can start to change temperatures again. Is this playing? Because I muted her, it's not doing much. So what's going to happen? They're going to melt this ice cube, and you can see it. The temperature comes up here, and then I guess I paused it. Temperature comes up, and as the ice is melting, your temperature is not changing. All the heat.
Teachers, pardon the interruption, you need to follow the seniors come down to the cafeteria.
Now it's probably this.
Skylar Harrison, Landon and Lane Hernandez, Damon Herrera, Juan Lopez, Alexis Payne,
Oh,
Alexa Pellerose, and Jose.
there you go. Now's your time to shine. Yeah, and seniors, no mask at pictures, but everybody else maybe the mask, just to commemorate the year, because this was the year we all wore masks. But yeah, you can see, you cool your ice. Not cool. I guess you're heating your ice up until it gets to freezing, 0 degrees Celsius or 32 degrees Fahrenheit. But while that ice is melting, it's not going to go above that freezing line. That energy just gets put into melting the ice. And the same thing, I'm heating my water up. When it gets to boiling temperature, it starts to boil, but the temperature stays flat until literally all the water has boiled off, and now it's turned into steam. Then my temperature can start to rise again. And so this is a pretty good animation if we watched it all and listened to the narrator talk. And then the last two here are just little videos. They have one on the principle of relative dating and one on mapping, which I really like mapping. And we're not going to have enough time to watch this today, although it'd be really close. Let's watch some of it. Let's see what they say.
This is the map that generations of school kids have grown up with. It's the famous Mercator projection. But Peter shocked the world when he announced that this map was quite simply wrong. He pointed out that Mercator was distorting the size of countries in an attempt to retain their shape. As a result, Europe looks far more prominent, whereas the developing countries are being downplayed. If we look at Africa and Greenland, they look about the same size. But Africa is actually 14 times bigger.
Y'all have heard this, right? Yes. There's no good way to make a map that's not like a globe. The globe's going to be close to the most accurate because any other map, you're taking a round thing and putting it on a flat surface. And so there's lots of ways to screw this up. The best map in the world is Australia's map, which has Australia in the center and the entire world upside down. And so you can Google Australian map and you'll see what I'm talking about. But they go full on Australia.
Just condemned this map as being imperialist and racist.
Peters was no cartographer, but he thought he had the solution. Taking account of the relative size of each country, he came up with a new formula for representing the globe on a map, and he called it the Peters projection.
Okay, and that's okay, because now everything is the correct size, but is that the proper shape? No. And so people from Texas will immediately be like, whoa, 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 whoa. You don't mess with the shape of Texas. We have tattoos, we got stickers. You can't just change the shape of Texas. And so every map's going to have its problems that people don't necessarily like.
Peters claimed his map showed the true size of countries for the first time ever. He dramatically reduced the size of Europe, whilst expanding the size of Africa, elongating South America. And it's still something of a shock to look at this map and see how large these two continents loom on the Peters projection. Peters regarded himself as a champion of what he called the non-white peoples, and he saw this map as part of a wider project to right the wrongs that he saw as being perpetrated against those people living in the developing world. Ira Peters invited nearly 300 members of the international press to the unveiling of his new world map. The media embraced it with enthusiasm, but professional cartographers were furious at what they saw as the cheek of this outsider. They called the map deceptive, absurd, illogical. They were clearly really annoyed at what they saw as an untrained cartographer trying to map the world, and they accused Peters of making a map that was full of errors.
Die kartografische Reaktion
The
war
reaction was
sehr
very
enttäuschend
disappointing for Arno
für
Peters.
Arno Peters und sie
It
stand
was
auch
in
in
sharp
einem starken
contrast to the great
Kontrast
enthusiasm of
zu
the
der großen
international press.
Begeisterung,
But he
aber auf
stayed
der anderen
optimistic
Seite
and said,
bietet sein
"This
Optimismus
map
uns
Well, if you're going to translate somebody, you got to bring their volume level down. I can't hear both people at the same
would
time.
prevail."
die
Our
Kap
teachers, we go ahead and send the following seniors down. Aaron Roberts, Ivan Salceda, Wesley Solomon, and Morgan York.
Karte wirklich
Because it will succeed
durchsetzen, weil sie
internationally.
international sich durchsetzen wird.
And the Peters projection did become an international mapping phenomenon. Anyone who wanted to display their liberal credentials pulled down their Mercator's and proudly replaced them with the Peters projection. It was championed by Oxfam, the United Nations, and the Catholic Church, and it sold more than 80 million copies across the world. But the Peters projection did have distortions of its own.
Despite all the success and adulation, the critics did have a point. The Peters projection was flawed, and it wasn't even accurate on its own terms. Peters had made some basic miscalculations, which meant that countries like Chad and Nigeria were twice their actual length. Did Peters ever accept that there were inaccuracies on the map?
War durchaus bereit,
He was certainly prepared to
Fehler
accept mistakes,
zuzugestehen, aber es hat ihn kein Argument
but no
überzeugt,
argument convinced
weil
him
alles
because everything
berechnet
had been
worden ist,
calculated.
jeder Punkt neu berechnet worden ist.
I mean, I know he's a map maker, but this guy has 3 globes behind him, and one of them's like the biggest globe I've ever seen. That's a pretty big globe. I bet it costs a decent amount.
Nach einer
Every
bestimmten
point had
Formel,
even been
die selber
recalculated
berichtet,
to a
die er
specific
selber
formula
entwickeln
developed
lassen
by
von
experts.
Fachleuten. Hat dann das immer wieder
He kept on
überprüft
checking,
und
and
es haben
no
sich keine
mistakes were
Fehler
found.
herausgestellt.
Arno Peters was attacking other maps for being biased, yet he was blind to the fact that the Peters projection was just as distorted by his own political assumptions.
But the Peters projection did do something quite extraordinary. It finally exploded the myth that maps can ever be 100% accurate, scientific.
Well, we got most of the way through. So, everybody have a nice weekend. I'm ready for it.